So the answer to the experimental question, there's three things you're asked to find. The first thing is you need to find the average acceleration of the athlete. You need to find out how long the athlete is accelerating and how much distance is covered during the acceleration. So what I'm going to end up doing is I'll have my athlete start at 0 and finish at 100. And I will have increments 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And as the athlete travels, every 10 meters, I'm going to record the time. So things I'm going to measure, my independent variable is distance, which I'll use a delta x, and the equipment tape measure would be fine to figure out 10-meter increments. And I'll measure time, which we'll use a t, and a stopwatch would be perfect. So the idea is I need to figure out at what point does the athlete spanning 10 meters and then another 10 meters and then another 10 meters, at what point do these all have the same time? Because if the time to travel 10 meters becomes the same for 10-meter increments, that means I've achieved a constant velocity. The velocity would be delta x over t, 10 meters over that same period of time. So if the velocity is constant, that indication is, well, you're not accelerating anymore. So that's how I can figure out two things. One is that's going to allow me to figure out what is the time for acceleration. And the second thing that will allow me to figure out is what is the distance for the acceleration. And ultimately, that will allow me to find the original thing when it says, well, I want to know the average acceleration. So I can do this by using the third equation, delta x is v naught t plus 1/2 at squared. I'm sorry, that's the second equation. V initial is 0. So once I know how far was required for the acceleration and how much time was required for the acceleration, I can solve for A. Now, to quickly recap, overall procedure, set up a 100-meter dash, and you need, it would be 10 people timing, one person at the 10 meter, one person at the 20, one at the 30, on and on and on and on. Everyone starts the watches at the same time. As the athlete crosses that individual marker, that individual stops their watch. So basically what I'm going to end up with is a data table that says delta xt, 0, 10, 20, on and on and on. Time would be recorded in the other column. So x is my independent variable, time is my dependent variable. At this point, I've kind of got this table filled out. I have a way to answer all three of these questions, and I have a procedure. I obviously did not write the procedure just in the interest of time, but I verbally told you what the procedure would be. And now it says, describe how the experimental data could be analyzed to determine the average acceleration of the athlete. So that's where this equation is going to come into play. Independent variable goes on the x, delta x in, meters. And here, time and seconds. But what I'm going to do is I'm going to do time squared because it's a t squared that relates to this. Taking this equation and rewriting it as t squared equals, t squared would equal 2 delta x over a. So since delta x is my independent variable and t squared is my dependent variable, once I plot a line, the slope of this line will be 2 divided by the acceleration of the athlete. Again, I stop delta x once I've reached this period in which the athlete has a consistent time spanning 10 meters. So that might be, say, 1.1 seconds. So from 30 to 40 it took 1.1. From 40 to 50 it took 1.1. 50 to 60, 60 to 70, 70 to 80, etc., etc., etc. If it keeps taking 1.1 seconds, the athlete has stopped accelerating and is now traveling at a constant velocity, their maximum velocity. So going through this just one more time, make sure to describe the experimental data. This would allow us from the data table to extract how much time was there for acceleration. If I find out that, hey, right here at the 30 meter mark, all of the 10 meter increments take the same amount of time, 1.1 seconds. So I would look to see, okay, 30 and then some time TA. This is the time required for the acceleration. This is the delta x for the acceleration. And I could have multiple points on my graph too, 10, 20, 30, and then time of those, the first time, the second time, the third time, and figure out the slope that way. But that's all I would graph. I would not graph the whole thing, because eventually this function would change in such a way that the acceleration is going to be 0. You'll end up with a constant velocity. Okay, so with that being said, include a description of any examples or equations. We did that. Data tables, graphs, other representations. We're good to go.